All right. Good evening. So here we are. Unit 6 test is tomorrow, and I just want to go through a few things with you, just like I like to do. So remember a couple things. Like it says up on the screen, be ready to take some notes, sort of be engaged with this. If you just watch, I mean, it's better than nothing, I guess, but you won't really get as much out of it if you just kind of have this on in the background. And yeah, so kind of be into this. Like, if you're going to spend the time doing this, I mean, you know what, having it in the background is better than nothing. But the more you put into this, the more you're gonna get out of it. So notes, whatever, I'm gonna go through each section of the test, starting with 6.1 and 6.2, 6.3. If at any time you have any questions, just send them via Remind or put them in the YouTube chat. I know the chat is public and you're probably logged in on your own personal account, which is, I guess, fine. But yeah, so Remind is probably the best way. So without further ado, let's just get into this. So we're going to start with some basics of electrostatics, understanding a little bit about how the atom is set up. Very important to understand how this works. So first question, identify the name and the charge of the parts of the atom. We're going to assume that B is neutral. So right there, we're going to assume that this is the neutral one because they're not labeled for hopefully obvious reasons. So you can just mentally think of your answer or but that is your, what do you think? If what is, I guess it says label each part. So let's take a look at what is A. So A is on the outside. This would be, it's not in the middle, right? So hopefully you know this, it's little. This is our electron. And it is negative. It's the only part of the atom that could actually leave because it's on the outside like that. Letter B then over here is the purpley thing. It is the neutral thing. It says it's neutral, so we're going to go with that. Hopefully you know that's the neutron. Let's see if I can spell this right. Neutron. I only get one shot at this. I can't even. And that is going to be not negative. Speaking of screwing up things, let's see if I could. There we go. So that is going to be our neutron. And neutral. Okay, it says B is neutral. That's how I knew. So going down the line, well, let's just skip letter C for a moment because letter D is pointing to its own little thing there, the green thing in the middle, the thing that's not neutral. And why is it? No, don't allow. Okay. I have a remind going, so yeah, cool. All right, yeah, all right, yep. The remind things are accurate. You guys are good. You guys are okay. I'm going a little too slow, maybe then. So this is the proton. Those are the protons. They are positive, and as some of you guys pointed out in the remind, C is talking about this whole thing in the middle here that includes both the protons and the neutrons, and that is the nucleus. Wow, I should type this stuff or something. And overall, because it only has the protons and the neutrons in it, that it is going to be positive overall. Okay, because it's got the protons and the neutrons. It doesn't have any electrons in the nucleus. All right, and so don't forget that the nucleus is the thing that it can't move. It can't move at all. They're stuck in there. All right. Just seeing, yeah, proton. Good. Awesome. All right. So from what we can see, which, whatever, it doesn't look like this atom is charged or neutral. Now, we got to go by what we can see, and we already said that B is neutral. So we could kind of count up what we see in the middle there. And it looks like we've got 1, 2, 3 electrons. Those are negative. And we've got, those are neutral. So the green things, 1, 2 in the back and 3 in the front. It looks like we got 3 and 3, which means that it is neutral. All right. And remind, you got it. Cool. I know there is going to be like a 5 to 10 second delay between me talking and you responding, and like like there's just a delay with YouTube. That's how it goes. It's YouTube. It's probably for the best, honestly. Okay, so charge or neutral. Let's assume for now, in chemistry you'll learn a little bit differently, but let's assume that an atom is neutral unless otherwise mentioned. Okay, neutral meaning it's going to have the same number of electrons as protons. All right. So if it does become charged, how? What has to happen? Which of the following will cause the atom to become charged? And it's going to be more than one, but not all of them. So going through, lose electrons. Will that possibly be charged? Yeah. These electrons right here, they can leave. And so, yes, losing electrons will cause it to become negative or positive. Think about this. Losing an electron, losing a negative will cause the atom to become positive because now it has one less negative charge. The balance is in favor of the positives. Gaining electrons, yes, that is possible. It could gain another electron. Something could just show up and like hang out right here. It's like, hey guys, what's up? In that case, that would make it more negative because now it has extra electrons. Letter C, lose protons. Protons. Okay, wait a minute. Protons is in the middle in this little area right here, right? Remember that these things cannot move. They're stuck. That goes for the neutrons too. So no, 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 no. None of those things can leave. Those are stuck in the nucleus. So the only thing that can happen is if you lose electrons, that causes you to become positive. Well, I could spell positive. I'm a wreck. Gaining electrons causes you to become negative. Or I should say, it causes the atom to become positive and negative. So, all right, moving right along. These are the easy ones. Why does a charged balloon stick to a neutral wall? Why does a charged anything attract a neutral anything? That's a question that you definitely need to know and be able to explain it and maybe draw a picture. So it says it's a neutral wall. So letter A doesn't even make sense. But you know what? I'm going to pause a second and let you think about this for a second. You don't have to put anything up there, but the chat looks like nobody put anything in the chat, so that's fine. I see stuff in Remind. It's probably for the better. Okay, the wall is not positive. It literally says it's neutral. So no. The wall becomes polarized. That's the correct answer. So okay, the wall loses atoms. No, the wall does not lose atoms. That doesn't, again, make sense. And the wall loses electrons. Well, that would make the wall positive, and that's not going to happen. The wall is an insulator. It doesn't tend to lose electrons. Yeah, it is B. All right, cool. And if you remember the FET simulation, I mean, it was one of the things that was on the intro screen to this. If you've got a balloon coming near a wall, and like here, so here's the balloon, here's the little string, and the balloon is overall more negative. Like maybe there's a couple positives here and there, but overall it's more negative. What's going to happen there? And I don't know, maybe you rubbed your balloon on some fur or your hair or something like that. Well, the wall overall will have just as many negatives as positives, but what starts to happen is the positives don't move. They're stuck, don't forget. And so what happens is the negatives get pushed away from the balloon. The simulation shows it a lot more clear than my terrible drawing right there, but that's basically what's happening. And that's what polarized means. Polarized means that overall it's still neutral. It's just that one side is more positive, so it's like this side is positive, and the other side is more negative because like the electrons are getting kind of squished together over there. Okay, think of like the north and south pole of the Earth. One side is north, one side is south. Magnets, same idea. All right. All right. My phone just went to sleep, so let me open it up in case I see reminds. When you rub a balloon on your hair, it becomes negatively charged. What happens to your hair? Read these. Take a second. And you could put it in the chat or just think about the answer. What would you choose if this was a quiz or a test? And tomorrow, that won't be like a hypothetical situation. Okay, letter A is significantly vague enough that should throw up a little yellow flag for you. They affect each other. All right, that's, we get a little bit more detailed than that in this class. So that's not going to be it. Plus, it doesn't become negative. Gaining protons. So, by the way, this is the frowny face part. This is the frowny face part about this. Gains protons. No, that cannot happen. Protons are stuck in the nucleus. They can't go. Nothing gains protons, nothing loses electrons, protons. They're stuck. Letter C is interesting, but that's not what happens at all. That doesn't happen at all. It's just not what happens. The answer is D. Your hair loses electrons. Your hair becomes positive, and the electrons that went over to the balloon, they have to come from somewhere. And so they come from your hair. That's the whole point of rubbing it in your hair. And so your hair loses those electrons to give them to the balloon. So the balloon becomes negative. Your hair now has lost electrons. And so your hair is more positive because it doesn't have enough, negatives to balance out the positives. Okay, moving along. Speaking of being balanced, an atom that has 33 protons has a -3 charge. How many electrons does it have? So just think about this multiple choice. That my little cursor being by the D means, there we go. I wasn't trying to imply anything. So let's talk about it this way first. If this is a proton, no, if this is the nucleus and it has a plus 33, it has 33 protons in the middle. That means that swirling around the outside, all those electrons, very good. If this is neutral, it's going to have -33. It's going to have 33 electrons, okay, to balance out. It's now neutral. So if it has a -3 charge, that means it has to have 1, 2, 3, and this is no way drawn to scale or really correctly. It's just about getting the number. And so if it has a -3 charge, that means it's got these 33 electrons plus these 3 additional party crashers that came in. And so yeah, on remind, you got it. The answer is 36. Okay, because it has to have the original 33 to cancel out the 33 protons plus 3 more electrons, which are negative, to make this the -3 charge. All right. I just dropped my pen. All right. And please send me questions if you have any. Oh, what are these things? All right. We love these things, right? How do I say this? Use the scratch paper when you do these questions. Every time somebody gets one wrong, it's not because you don't know what you're doing. It's because you didn't do it all. Like here, let me show you. This is what happens, and this is what I see all the time. Okay, okay. Oh wait, well this one is there. Interesting. Oh, okay, I see. Y is negative, and we want to know what balloon Z could be. So Y is negative. Definitely, that is given, right? So what we typically do, or what I see happen all the time, is like, all right, Y is negative. That means X must be positive because, well, it is, or it could be neutral because it could be attracted to it. Okay, either way, positive or negative. Here, let me just I'll write it down what I see. So X could be positive because opposites attract, and it could be neutral. So far, I've seen that, and that tells me you know what you're doing. Okay. So here's what happens. You write this over there, positive and neutral, or maybe you're just thinking this because so far that's easy to keep track of. And so what I see is, all right, well, this is repelling it. Well, see, this is, It would be a little bit different case if it was attracting it, but in this case, it's repelling it. So you look at what happens is I see people look at the positive, but you forget about the negative. You forget about the neutral. You got to do both choices, basically. And this is kind of a bad example of that one. So really, the only answer is Z can be positive because it's repelling it. And if X is neutral, they wouldn't repel anything. This is not possible. So this is just, okay. Bottom line is, if you've been having trouble with these balloon things and you keep getting them wrong, write it down. Write it down and make sure you do like, all right, if is positive, then it could be positive. If it's neutral, then what could it be? All right. And in this case, it can't be neutral because neutrals don't repel each other. Okay. But that's my advice to you, is to write it down. Use the scratch paper with these. Don't be afraid to. It's an easy question. And everybody I've seen knows how to do it. And it's really a shame if you get it wrong because you tried to cut a corner and save yourself like 5 seconds. It's just not worth it. Okay. All right. And I don't have any balloon questions, but I could, yeah, we've talked about this in class. All right. Object A is positively charged. Object A and object B attract. Object B and object C repel. Object C and object D attract. What type of charge might object D possess? Check all that apply. All right. This is an extended example of the balloon question. My phone keeps going to sleep. So what do? Write them all down. A, B, C, D. Okay. Object A and object B attract. Okay, it says object A is positively charged right away. We're going to just, okay, we know that. That is given. It says object A and object B attract. Okay, a positive will attract a negative, and it will also attract a neutral. Okay, we got to keep both in mind. Object B and object C repel. All right. Well, if object B is negative, so I'm going if it's negative, and then I'm going to go if it's neutral. And this is what you got to do, is why you got to write it all down. If it's negative, then the only thing that's going to repel a negative is a negative. Nothing will repel a neutral, so honestly, this can't even be neutral. So what that means is C is definitely negative. All right, this one's an easy one. Object C and object D attract. Okay. What's going to attract a negative? A positive and a neutral. All right. So it looks like it is going to be positive and neutral. Nice job. Positive and neutral. All right. Like I said, just like with the balloons one questions, take the extra few seconds and write this down. All right, make the list, write out all the possibilities, and take your time on these. Don't forget them. All right, don't rush through these. I would call these maybe medium to easy. All right, these are easy, and then there's medium easies. So take a minute, because don't get a medium run wrong because you're trying to save a few seconds. All right, you know what you're doing with these. And if you want assistance, I could maybe help you out. All right. So that is electrostatic. It's the introduction. There's obviously more. There's Coulomb's law and all that. But I'll wait a second because we got that like 10-second delay. So I'm kind of stalling here. Apologize. I'm sipping my my warm tea because it's March 8th and it's freezing cold out, which I'm okay with. I like the cold. All right, moving along then. Whoa, hello. Let's do it this way. It's skipping from slide 10 all the way to, there we go. That was weird. I don't know why I did that. I'm like, I know I didn't delete 20 slides. There they are, okay. This stuff should look kind of familiar to you here. If the distance between two charged objects quadruples, what happens to the electrical force between them? And I'm just going to say this right off the bat. If, let me get my pen back up. If you see a word like quadruples and you don't know what it means, please don't hesitate to call me over. You probably know that this means 4, but if you see like centuple or tripled or whatever, halved or quartered, you know, if there's a word you don't know, call me over. If I can't help you, I'll tell you. If it's like, well, you should know that word, then I'll tell you. But maybe I might, this is not a vocabulary word. Okay, so it quadruples, meaning it is 4 times the distance. Okay, there's 2 things we got to keep track of. Distance is one of them for electric fields when it happens to, when we're talking about Coulomb's law. When the distance changes, what's the answer? Well, hi, Nikki. It's funny, Nikki. It's too bad that all you got from me last year was this. It's a shame. This was supposed to be different. All right. Anyway, I'm getting distracted. Distance it follows the inverse square law, right? Inverse square for distance. Okay. This applies to the gravity thing too. So gravity, for both Fe and Fg, both of them, if distance changes, it follows the inverse square law. Okay. What that means is quadruples. That's 4, right? So inverse means you take 1 over it. So 1 over what you got. So you flip it over, it becomes 1 over 4th. Then you square that thing, and 1 squared is 1. 4 squared is 16. So it is 1/16. All right. 1/16. Inverse square. All right. Same question. No, maybe. There's a difference. There's differences. What am I asking here? The distance between the charge objects is now 1/4 of what it was. What happens to the electrical force between them? Similar, but now backwards. It's the opposite. The opposite thing happened. It got smaller. It got smaller. Smaller is not a word, but it got smaller. Okay, it got shorter. So it is talking about distance. So whenever you see the word distance, inverse square. When it comes to these 2 things, electric fields and gravitational fields. All right, remember the whole spray paint example, things spread out more. So inverse square, inverse of 1/4. So 1/4 becomes 4 over 1. Okay, that's the inverse. We could ignore the 1 now because it's on the bottom. And then we square that, and that becomes 16. So this becomes 16 times the force, the electrical force. Fe is electrical force. Okay. Next question. If the charge of one of the objects is quadrupled, what happens to the electric force between them? Okay, there is nary a distance anywhere to be seen. There's no distance mentioned, right? Now it says, what's changing here? Look, the charge is changing. Okay, in this case, it quadrupled. It went from 1 charge to 4 charges. All right. What happens to the electrical force? Charge is, what's one? Let's just land on something here. We'll just call it direct. It's a direct relationship. You could call it's proportional. It's a directly proportional relationship where if one goes up, the other one goes up. If one goes down, the other one goes down. So for charge, aka Q, and also for mass when we're talking about gravity. Okay, so we're talking about charge right now. So charge is quadrupled, therefore it's 4 times the force. All right. It's got 4 times the charge. It's going to get 4 times the force. All right. If the charge of both objects is quadrupled, what happens to the electrical force between them? See, now we're getting a little bit more complicated. It's the same idea, but now it's like, all right, now we got like, I'm assuming you know what's going on with this. Okay. We're talking about charge. Okay, not distance. Which means that if you go from 1 to 4, this is going to be 4 times the charge. This is also going to be 4 times the charge. And they multiply. So you multiply them together, 4 times 4 is going to be 16 times the force. Okay. It's still proportional each, but Okay, this is a question that is kind of out of nowhere. Which one shows an inverse square relationship? Well, inverse and square, two things. Inverse means that if one side goes up, the other side goes down. Okay, you flip it over. 2 becomes half, 3 becomes a third, 4 becomes a fourth. So the one side is getting bigger, 2, 3, 4, and the other side is getting smaller, half, a third, a fourth. Okay, so that eliminates A because that's going upward. It also eliminates C because that's going upward. Square is not linear. It's going to be a curved line going down, inverse square. All right. I know it's out of nowhere, and this is not something we've talked about a lot. It might have been on the review guide, but it was mentioned once. Okay, but this is just what a graph looks like when you have an inverse square. Okay, just remember, square, you're going to get like a curvy line like one of these two things. It's just, you've done graphing x squared. Inverse means that if one goes up, the other one's going to go down. So it has to be, it has to be D. It has to be negative. All right, we'll do it with that one once you can. All right, this is, I believe this one is almost definitely on the review guide. All right, so what do we do with these ones? And I went through it on the board once, maybe twice. How do we do these? It's pretty straightforward. You just got to remember those two things. There's two things to consider: the charge, okay, the Q, and the distance, okay, the D. And we keep in mind that the charge is a direct relationship, okay, and the distance is inverse square. I'm gonna have like dreams about inverse square. Okay, so we gotta look at both of those on these types of things. And so we'll do the charge first. I think last time I did the distance first on the board. So we have a +4 charge, so that's gonna be +4. It's gonna be 4 times as hard. It's gonna push with 4 times as much force. Okay. And now this is where we multiply because this is taking them together. Now we gotta look at the distance. This is 2 units away from the other charge. And yeah, this is negative. It doesn't matter if it's pushing or pulling. That's not what it's asking. So it's 2 units away. Because it's the distance, we have to do the inverse square. So 2 becomes a half, and then a half you square it, and it becomes a fourth. And so when you multiply those together, you basically get a total of 1, because 1 times a fourth is 1. So relative strength of 1. Okay. This one down here, it's got a +8, or it's got 8 charges, so it's going to push with 8 times the amount of force. It's 1, 2, 3 units away. So do the inverse of that. So it becomes 1/3. 1/3 squared becomes 1/9. Okay. And so when you do that, it's 8/9. That's something. 0.88, right? That becomes 0.889, we'll call it. All right. Now really quick, just to kind of recap a little bit here, the inverse square, okay? I'm just gonna call it the inverse square. It goes like this. If there's a distance and the force, okay, and I did this on the board, but you know what, I'm gonna recap it really quick. One distance, 1 unit of distance is gonna be 1 unit of force. All right, it's pretty straightforward. 2 units of distance, so if you double the distance, that's gonna be 1/4 the force. Inverse square, okay? 2 becomes 1/2, square it becomes 1/4. 3 times the distance, I guess I'll put little x's in front of it to indicate times. Okay, so 1 times 1/4 of 4. So 3 times the distance is going to result in 1/9 of the force. 4 times the distance, quadruple, will result in 1/16 times the force. Okay, this is the inverse square law. The flip side of that is half the distance. So half times the distance will result in, all right, so flip that over, becomes, so inverse of half is 2. 2 squared is 4 times the force. Okay, 4 times the force. That's supposed to be an x. 1/3 of the distance becomes, flip that over, becomes 3 over 1, becomes 9 times the distance, and so on. So 1/4 becomes 16, 1/5 becomes 25, okay, dot, dot, dot. So we went over that we took notes on that. Hopefully you wrote that down, but if not, it's right there. So when I'm doing all this stuff here, this is gonna be 2 because of the charge, and then it's only 1 unit away. So 1 becomes 1, I guess, right? We're just, that's what it is, 1 unit away. The inverse of 1 is 1. The square of 1 is 1. And so we basically get a 2 for comparison purposes. This one over here is 12. That's a big one. Let's see if that makes a big difference here. We are 1, 2, 3, 4 units of distance away. 4 becomes 1/16. And 12 divided by 16 is 0.75. So now we just compare the numbers because it wants to know the most electrical force. Which one has the most electrical force? It looks like C does. It's got twice as much as anybody else, as the nearest competitor. Okay. I think there's one of these on the review guide. So, oh, and hopefully you get one like this. Well, which one has the least electrical force? It's the same questions. So all we gotta do is say, all right, which one has the smallest number here? And it looks like letter D. So that has a 0.75. So letter D has the least electrical force because it had 0.75. Okay. So yes, I'm getting into some of the more interesting or difficult questions, but that's sort of the point of this review, right? All right, just open up my what do you call it? Wake up my phone. Oh, yes, 1/16. Yes, yes, yes. All right, cool. There's more, but wait, there's more. Yeah. All right, nice job, you guys on Remind. Keep that up. Keep that up. All right, you guys are doing great. Okay. Oh, hey, what's this one? All right. So we have a small negative charge here in the middle. There's like 5 situations, A, B, C, D, E situations. They're all labeled. They're all 1 negative charge in the middle, and it's placed by much larger charges. So in which situation would the small negative charge experience the strongest electrical force? It doesn't say anything about positive or negative, push or pull or anything like that. We just need to figure out which one has the strongest electrical force. So this one's going to take a little bit of analysis once again. So we have to look at the 2 things. So we got 3. Letter A is a +3, and there's no like little lines. So look, it looks pretty like this looks like 1, 2. And this looks like 1, 2 in the opposite direction. Okay, so we'll kind of keep that in mind here. So this is 1 unit in the opposite direction. So it looks like this whole thing is experience a force of +3 units. Okay, so whatever that means. 3 times 1. Letter B, there's nothing over here. This is a -6 over here. Oh, and yeah, let's just get some numbers first. So -6. And it's 1 unit away. So let's just call it times 1. We're not really going to worry about the negatives at this point. So this one has experienced a force of 6 units of force. Okay. Now to quickly compare, this 3 here is a positive. So it's going to actually pull it this way. It's going to attract it. These 2 are both negative, so this is also going to be pushed in that direction, but that doesn't really actually matter. I'm just pointing out the direction, what's going to happen, what direction is going to get pushed. Okay, now letter C is a little bit different because we got 2 things going on here. One is a positive, one's a negative. One is going to pull and the other one is going to push. So now we kind of do have to keep track of the direction. And bottom line is they're just going to cancel each other out a little bit. So let's keep that in mind when we're doing this. So we got 3 because of the charge. It's a +3. and it's 1 unit away, whatever that means, because that's just we're using it. So this is a it's got a push or pull of +3. It's pulling, in other words, to the right, because it's a positive. It's attracting this negative. This one is -3, so it's going to actually be repelling. Let's see with how much strength though. So it has got a 3 charge, and it is 2 units away, which means using the inverse square law, it's going to be pushing with 1/4 of the force. So 3/4. I don't know why I grab my calculator. I just tend to do that. So 3 times 1/4. This one's going to be pushing with a force of 3/4, which is 0.75. So we could think of it this way. This one is positive because it's moving it, pushing it to the right or pulling it to the right. This one is negative because it's pushing it to the left. So overall, number C, letter C, is, we got to do a little subtraction. It's going to be 2.25, it looks like, to the right, okay? Because it's got 3 to the right and 0.75 to the left. So while letter A is feeling 3, letter B is feeling 6, letter C is only feeling 2.25. Okay, I told you this is probably one of the more complicated ones of these ever. So if you get a little lost, just later on you can rewind and watch this again. And then, send me reminders if you got questions. Letter D is kind of in the similar boat. We got 2 things going on here. We got to keep track of both. So the charge of this one is 3. The distance, it's got 2 units away. Doesn't matter. It's over here. It's a number line. If you want to keep track of negative, doesn't really matter. So it's 2 units away. That means inverse square law is going to be 3/4 again, or 1/4 again. So it's going to translate out to 3/4, which is 0.75. It's a negative charge. So how is that going to interact with the negative charge over there? It's going to repel it to the right. It's going to push it to the right. So 0.75 to the right. This one over here is got a +3, a 3 charge. Because of its charge, it's got 3 times as much force. And it's only 1 unit distance away. So we're just going to multiply it by 1. The inverse of 1 is 1. The square of 1 is 1. And this is going to be 3 over here. Now this is a positive, and it's going to attract this negative. So strangely enough, it is also going to be pulling the letter D to the right. Got a question or something? Never mind. Let's see what you got. I'll come back to that. All right, let me finish this one. So this is 3 to the right and 0.75 to the right. So letter D is actually feeling 3.75 to the right, because they're both causing the negative to go to the right. I know, right? This one, I kind of regret putting my numbers here, so let me just erase those really quick. This one's got a 6. I'll just squeeze it over here. 6, and it's got 2 units. All right, I'll put the unit numbers back there. It's got 2 units to the left. So because of the inverse square, that means it's going to be 1/4, 1/4. I don't know 6 divided by fourths. I probably should, but 1.5. I thought about that for even 5 seconds. 1.5, and it is negative. And so that's going to actually pull it to the right. It doesn't matter. There's no other things involved here. All right, so let's just kind of take stock here. This one over here has a +3. This one has a +6. That looks like the strongest so far. This one has a 2.25, letter C. Letter D has a 3.75, and letter E has a 1.5. So which one is the strongest? You're gonna be tempted to just guess on this one tomorrow, but maybe come back to it. Flag it like you can and come back to it. So which is going to experience the strongest electrical force? It looks like B is our winner with 6 by far. All right, I got a question for electrical force with the number line looking things. Why was C considered having the highest if C was -2? All right, I'm going to go back to this one. Great. -2. So why was C the highest? I might have misspoke. The answer, and I'll go back to the other one. You got to watch out. It just says the most electrical force, not the highest. Because if you say highest, that implies it's positive. All right. So the largest, maybe is a better way to say it, which experiences the largest electrical force. And yes, this is a -2, but it wasn't asking which direction. All it's saying is which one had the most electrical force, the largest electrical force. So it is going to be attracting it, because they're negative and a positive, it's going to be pulling toward each other. But I hope that answered the question. In theory, it could ask which one has the strongest to the right, I guess, or positive electrical force, but it's not asking anything about direction in this case here. All right, cool. All right, so this one, it could be a hot mess. Like I said, come back and check it out. If you have any questions, rewatch this part and see how I combined. I just kind of made up the numbers on the bottom because they were kind of like 1 and 2 apart from each other. And then I combined the charge and the inverse square for the distance. And then I considered, was it pulling or pushing? All right. So like, especially compare not letter B, not that one. Especially compare letter C and letter D. See what I did though? Those are the special cases. Those are the crazy ones. Okay. The other ones, A and B and E, are very much like the previous one here. Okay. So, but it's letter C and D that were the crazy ones if you want to go check those out. Okay. Hopefully a more straightforward one, right? According to Coulomb's law, which of these are true about the relationship between electrical force, charge, and distance? Choose all that apply. Is force directly related to the distance between charges? Letter A. Letter B, force is related to the inverse of the square of the distance between forces. Force is directly related to the magnitude of the charges. Force is related to the inverse of the square of the magnitude of the charges. Okay, when you see a question like this, it looks horrendous. There's a lot going on. But what I'd recommend you do is break down, okay, all of them have force. Force. Okay, there's no differences for those. It's talking about force. Letter A is talking about charges. Letter B is talking about distance. Letter C is talking about charges. And letter D is talking about charges. Okay, that's your clue. Those are your clues right there. So let's look at the one that isn't like the others. Distance, right? Letter B. Force is related to the inverse of the square of the distance. Ooh, that's inverse square right now. There's distance. Yes, distance is inverse square. This goes back to like 20 minutes ago when I was talking about that. Okay, so now look at the charges. What do you know about charges? Is it directly related? Is it, oh, I'm sorry. Oh, wait, there's the word distance right there. Well, hang on. Do we ever talk about distance and charges at the same time and directly related? No, we don't. We don't talk about any of that stuff together. Not when we're talking about like, not in this way. Okay. So charge, is it directly related to the magnitude of the charge, or is charge related to the inverse square? Well, charge is not inverse square, so it's not D. Charge is directly related, so it's C. Okay, so look for those little key words. Okay, charge and distance together is sort of like a weird thing when we're asking about these. So look for those little key words when you see a wall of text like this. When you see a lot of words, a lot of reading, look for little clues like this. All right, this is as close as I'm going to get to. Well, math and slideshows don't work very well together. And especially math and live streaming is a little rough. So I'm going to keep this as simple as possible. What is the force between those two charges if they are 2.5 times 10 to the negative third meters apart? Okay. Well, let's break this down. It says blah, 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 4.0 charge. Okay. Charge is Q. This one is 5.0 times 10 to the negative eighth coulombs charge. There's another Q. So we call that Q1 and Q2. Meters, well, that's a distance. Okay. And hopefully on the back of your equation sheet, that rings some bells because that has to do with this equation right here. There's your Q1 and Q2 and your distance. Okay. If you remember K on the front page, K is the charge constant, 9 times 10 to the ninth. Something to keep in mind. Okay. So what is the force? Well, it's not going to be A because we've got more than one Q. I never mentioned E or N, so no. The other three, they all do use those equations, the correct equation. But when you actually plug it in correctly, you'll get this answer. Okay. I'm not going to go into how that all works right now. Just I feel like I've done that in class. If you need help with the specific math stuff, please let me know, or come in early tomorrow or something like that. It's a little late in the game for that, but I mean, better late than never. So work through that, and this is where you're going to have to do like all those parentheses and the E buttons on the calculator. So let's see. So this is the one where it's like, on my calculator, there's an E, where'd the E button go? Oh, there it is. In this case, if you're watching on a little screen, it's a little hard to see, and this isn't gonna help because it can get all fuzzy. There's my little EE right there. Okay, so for this calculator, I had to hit that yellow button that I believe says second, but it's a little fuzzy. So like I said, though, we've talked about this a lot. And so yeah, there's not a lot I can say right now on the live streams that's going to be helpful and not drag this out indefinitely. So let's move on. So that's definitely something to practice. This is a little bit more advanced version of that question. What is the distance? Now we're trying to solve for distance between two spheres, one with a charge of 2.5 to 10 to the negative 6 coulombs, and the other with a charge of 3.5 times 10 to the negative fifth, when the force between them is 0.5 newtons. Okay, now, just, so this will be your force. This will be one of the charges, let's call it Q1, and this will be the other charge, Q2. So which is it gonna be? Well, this equation, as you see it written, they're all the same. That is the rearranged version of the previous equation that you need. So assuming you plug in those numbers correctly, and we've done stuff like this before, this is not your first rodeo with this kind of stuff. Assuming you plug in all the numbers, you should get B. All right. I suggest that you try this out, come back to this part and try it out. We're what? 50 minutes in, 49 minutes in. So you're gonna have to scroll ahead to 50 minutes and find this part and try it out. All right, make sure you get the right answer. 50. Okay, we are at 50 minutes. All right, 50 minutes. Okay, that's where we're at. So come back to this. Okay, electric fields. My general tips there, you ran into this question, and honestly, as long as, oh, hang on, something on, did we have to use the EE button or can we? Okay, do you have to use, so going back to this question, do you have to use the E button on your calculator? No, you do not. If you're okay with using the caret or whatever other method that you have on your calculator, please do that, whatever works for you. The E button, I recommend it. I think it's something you want to try to get used to using, but I'm not going to require it, no. All right, use whatever method works. When it comes to these, the rules are essentially these, and I've talked about them. So as long as you can do this, as long as you don't break these rules, you're fine. All right, don't cross the lines, and the arrows should point away from positives to negatives. All right, those little steps, I like to do those for myself when I'm drawing these, but you know, we didn't spend much time like actually drawing these out. I just kind of like to do it for, I don't know, for fun is the right way to say it, but basically it goes away from the positive. Oh, hang on, Mr. Jern. Not only does it go away from the positives, It goes toward the negatives. What? Yeah, so away from positives towards the negatives. Okay, straight out away from one positive and toward the negative. Something like this. What? There's a whole nother negative right down there. Away from the positive toward the negative. And there's ways to do this that are a little bit more accurate, so to speak. However, as long as you don't cross the lines and your arrows always point toward the negatives, and it shows some general like idea about what's going on. Now, they're not going to cross because they don't go toward each other here because they're both negative. As long as you basically do, well, that might actually curve back away from that might be the other one. So it's fine as long as you don't break those rules. Don't cross the lines and make sure the arrows point away from positives and toward the negatives. All right. Positives. They look like arrows that are pointing away anyway. It's like, hey, I'm a positive. Hey, what? I'm leaving. Okay, negatives. I don't know. I'm just trying to come up with fun. So, you've been sending questions on the Remind. I've been trying to answer them. So, continue asking questions. But I'm going to move on because I want to talk about gravity. Because why not? Okay. Oh, I mentioned in one of my classes my tea. This is my tea cover thing that you cover the tea with. You've heard me slurping on my tea, so I got tea. And yeah, this keeps the tea warm. This is what I've become. This is what remote learning did to me. I drink a lot of tea now. So, gravity. Which of these does not exert a gravitational force? Hopefully you've been kind of reading that as I've been, there's a word, as I talked about my tea thing. A black hole. No, that exerts a force. Yes, all the mass is there. The sun. Yeah, anything with mass will exert a force. It is a lovely tea cover. I know, and it works so well. Thank you. It actually, you know, when it gets really cold, it works as a hat. The Rosetta asteroid. Well, that sounds like something that has mass. So you have mass, a fly has mass, a speck of dust has mass, a proton has mass, an electron, tiny bit of mass. So it's a trick question. Anything with mass has gravity, okay? So none of these is the answer. We could argue back and forth about electrons, perhaps. So that won't even be an option on a test, okay? Because let's just say it has a tiny bit of mass, because, yeah, any kind of matter has mass. We'll leave it at that. And gravity. Which of these are true about the relationship between the gravitational force, mass, and the radius, or the distance from the center? Choose that apply. Radius is just another word for distance, because we're talking about, like, here's the center of something. It's like, well, okay, so that's the radius of, you know, like we talk about something that goes out in all directions in a sphere. Well, okay, that's that when you start talking about the distance from the center of something, that's a radius. So that's why you'll sometimes see the radius as instead of distance. So what is it? Well, force is directly related to the distance between the objects. No, force is never directly related to distance. You see the word distance in this context, you should automatically think inverse square. Force is related to the inverse of the square of the distance between objects. There you go. There you go. But wait, there's more. Force is directly related to the mass. Probably, yes. Instead of charge, now we're talking about mass, directly related. Yeah, I'm just going to circle that because that's true. Because looking at this, force is related to the inverse of the square of the magnitude of the mass. No, that's not true. Not true at all. Okay. Once again, and I'll be brief here, mass is direct relationship. Again, proportional. I think I said in the other a couple slides ago. Distance is inverse square. That, just remember that, okay? An inverse square is that whole like 1 over whatever thing. Which, if you don't know that, go back to that chart from 20 minutes ago. Okay, the Earth's mass is 5.98 times 10 to the 24 kilograms. What is the mass of the moon if it is 8 of Earth's radii from the Earth and it feels a force of 2.0 times 10 to the 20th newtons? What? All right, hang on. So we've got Earth's mass. We'll call that M1. No, not MI. M1. What is the mass of the moon? Okay, well, we could call that M2. If it is, well, 60 of Earth's radii. All right, hang on, let's come back to that one. It feels a force of 2.0 times 10 to the 20th. So that's going to be our FG. Okay, now this is an odd one, and this is going to be, how do I put this? Here, let me show you something. In the constants, we got the mass of the Earth. I don't know if you saw this. The radius of the Earth is right here. 6.38 times 10 to the third meters. 6.38 times 10 to the third meters. That's the radius of the Earth. 6.38 times 10 to the sixth. 6.38 times 10 to the sixth meters. And I say that because I don't have it memorized, and I'm pretty sure I'm right. 6.38 times 10 to the 6 meters. All right. I'll put that up on the screen during the test, but it's also on your equation sheet. That is Earth's radius. Okay. It's on the equation sheet. 60 of Earth's radius is how far the moon is from the Earth. Okay. That means that the distance is 60 times 6.38 times 10 to the sixth meters. This is one of those like real world questions that we need to worry about. So it's 6 of those, 3, 8. E, or times 10 to the sixth. So of course mine didn't put it in scientific notation, so I'm going to switch over really quick and change it to scientific notation. Hey, if your calculator ever gives you a weird answer and you want to know how to switch modes, please let me know. I can easily show you that. It is not hard. So 3 times 10 to the 8th meters. So that is the distance the Earth is from the center. That is the distance the moon is from the center of the Earth. Okay. So we now know the force of gravity. We now know G. We know G. You know G. Capital G. All right, capital G. You forgot G. That's cool. That's fine. It happens. That's why it's on the equation sheet right there. Okay. Capital G. It's on the equation sheet. Everything's on the equation sheet. Anything having to do with the equations, guess what? On the equation sheet. Okay. So there's G right there. Okay. So we know G. Where we at? So we know G. I'm using my pen. We know M1. That is the mass of the Earth. M2, I guess these should all have little 2's by them because that's what the equation sheet says. I mean, I'll double check, but let's see. Where's it at? There it is. Yeah, there it is. M2. So mass 1, Earth. Mass 2, Moon. You can switch them. It doesn't matter. So we know, well, no, we don't know M2. We now know the distance squared. We take this. This is our distance from the center of the Earth to the moon. We square that, and that'll be the bottom of the equation. Okay. We had to solve for M2. So how do we do that? Well, you have to do some rearranging. I'll do it really quick. Although to be honest, this is something you should be able to know. I believe the answer is B, by the way. Okay, so where are we at? We're near the end. This is going to be the last thing I think we talk about. So this is something you want to try. So to solve for m, let's see, we're going to start with fg is g times m1 times m2 divided by the distance squared. Okay, I want to get m2 by itself, so I'm going to multiply this by d squared. That's going to cancel out here, and whatever I do to one side, I've got to do to the other. So that all becomes d squared times fg is equal to g times m1 times m2. Okay, I want to get m2 by itself, so these are being multiplied, so I will divide to cancel those out. G and m. Whatever I do to one side, I had to do to the other side. So now m2, and I know I'm going fast, but this is YouTube, you can rewind it when you're ready, becomes d squared times fg divided by that constant g times m1. So if I use this equation with these numbers that we found, you should get 7.3 times 10 to the 22nd kilograms. Okay? Try it. Let me know if you have any questions on that. Okay, speaking of which, that's essentially it. If all that stuff looked familiar and you're able to follow along, you're in pretty good shape. There's nothing new. Okay, so it's 8 o'clock. That's not a bad time. We went through this pretty quick. There were some questions, but hopefully that was helpful to you. Go back through this. You could skip around now. Well, I'm going to end it in a few minutes. You can skip around and go to the parts you need to go to. All right. Send me reminds if you got any questions. I will gladly help you out. All right. All right. Well, good luck. Study hard. You're going to get out of this what you put into it. Okay. You will get out of this what you put into it. All right. Cool. You guys have a great evening. I will see you tomorrow. Take care and good luck.